Welcome to the Explainer. Let's just go ahead and acknowledge the elephant in the room right off the bat. Looking at a complex algebraic equation can be absolutely terrifying, right? It just looks like a completely messy alphabet soup of numbers and letters. But what if I told you we could build a logical, systematic master toolkit to tackle literally any complex equation that comes your way? This isn't just about math. It's really about developing the ultimate skill of reverse engineering complex, real-world problems.
Okay, so let's dive into this. How do you solve an equation that looks completely impossible? We're going to treat factoring not as some tedious homework assignment you just have to get through, but as the ultimate cheat code for reverse engineering math puzzles. It's how we strip away all that terrifying complexity to find the simple, beautiful truths hiding underneath.
Think of expanding an equation as baking a cake. You mix your ingredients together, in this case x minus 2 and x plus 3, and you bake them into a finished product, x squared plus x minus 6. But factoring is the magical ability to unbake the cake. You start with the finished product, that x squared plus x minus 6, and you figure out its basic raw ingredients so we can actually work with them.
Now, the whole reason we want to unbake this mathematical cake comes down to this absolutely crucial concept, the zero product property. It simply states that if A times B equals 0, then A equals 0 or B equals 0. This property is our absolute ultimate goal. If we can break a messy, expanded equation down into multiplied, bite-sized pieces that equal 0, finding the actual answer becomes incredibly simple. Because, 0 multiplied by anything, a circle, a triangle, whatever messy variable you have, is always going to be 0.
To get there, here is the visual blueprint for our master toolkit. First, Rule 1, find the GCF. Second, tackling trinomials and quadratics. Third, special cases and shortcuts. Fourth, grouping and substitution methods. And fifth, the ultimate backup plan. This whole thing is organized strictly by the anatomy of the equation, so you're always going to know exactly which weapon to pull from your toolkit.
Let's start with Section 1. Rule 1. Find the GCF.
The greatest common factor, or GCF, is simply the largest number or variable that can be evenly divided from every single term in your expression. It's the skeleton key. By pulling it out to the front, you instantly simplify the chaos. Take something like 12x squared plus 18x. If you pull out a 6x from both of those, it leaves a much friendlier 2x plus 3 behind in the parentheses. Instant simplification.
So here's how you do it every single time. Step 1. Break your terms down into their smallest possible factors. Step 2. Identify the common elements shared by all the terms. And step 3. Just factor out that GCF to the front of a set of parentheses. Whether you're pulling out a simple number or a complex term like 5x squared from a super long, messy polynomial, you're immediately reducing the size of the puzzle you have to solve.
All right, moving right along to Section 2, tackling trinomials and quadratics.
Once you've checked for a GCF, if your equation has exactly 3 terms, you need to grab the tools from this part of the decision tree. For simple quadratics, where the leading coefficient, that invisible number right in front of your x squared, is exactly 1, you just play a quick, fun number game. You just need to find 2 numbers whose product equals c, the last term, and whose sum equals b, the middle term. For instance, -7 and +2 multiply to -14, and they add up perfectly to -5. Boom! You write your factors out and you're practically done.
But wait, what if that leading number isn't a 1? What if you have some stubborn number ruining your otherwise simple problem? Well, enter the slide and divide method. First, you take that leading a term, slide it over, and multiply it by your c term at the end. This magically and temporarily converts your equation into a simple case. Second, you factor that modified expression just like we did a second ago. And third, you divide your new factors by that original a term to balance the whole thing out. It completely removes all the guesswork of trial and error.
Which brings us to Section 3, special cases and shortcuts. This is where factoring gets really fun. Once you train your brain to recognize certain mathematical patterns, you can skip all the hard work and just use these built-in power-up shortcuts. If you spot a difference of perfect squares, like x squared minus y squared, you can immediately rewrite it as x plus y times x minus y. There's no middle term to even worry about. Or if you see a perfect square trinomial, you just look for the square and double pattern. If the first and last terms are perfect squares, and the middle term is exactly double their product, you jump straight to the answer. It is a massive time saver.
Now, what if you run into intimidating cubed variables? Seriously, don't panic. If you have the sum or difference of perfect cubes, you just use the mnemonic SOFS to build your factors without breaking a single sweat. SOS stands for square the first term, opposite sign, first times last, always positive, and square the back term.
So how do we actually apply this in the wild? Well, step 1, you simply take the cube root of both original terms to get your short first factor. Then, step 2, you systematically apply that SOFAS acronym to that first factor to construct your longer second factor. By doing this step by step, you can easily unbake something as terrifying as x cubed plus 216 into perfectly organized parentheses. It works every time.
Okay, section 4, grouping and substitution methods.
Let's see how this builds when you bring out that heavy artillery. If you see exactly 4 terms in your polynomial, it's time for grouping. You essentially chop the equation right in half, you look at the first 2 terms and pull out their GCF. Then you look at the last 2 terms and pull out their GCF. If you do it right, the expression left inside the parentheses for both halves will match perfectly. And watch this. Those matching parentheses miraculously become your new massive common factor that you can pull out to the front. It's an absolute magic trick.
Speaking of magic tricks, let's talk about substitution. When you're staring down an impossible exponent, like an x to the 4th power, or maybe x to the 6th power, it looks completely unsolvable, right? But we use substitution to literally temporarily disguise the complex variable as a simple letter, usually u. We just pretend x squared is actually u.
By temporarily shrinking the problem down to size with this substitution, you'll notice that your massive, scary equation now looks exactly like a normal quadratic. So you factor it using the normal rules we already talked about. And finally, step 3, you just reverse the substitution. You swap the original bigger variables back in for u at the very end to finish solving. It's totally brilliant. You're effectively hacking the equation.
And finally, section 5, the ultimate backup plan.
Look, even with a master toolkit, sometimes an equation just refuses to be factored nicely. It's stubborn, and that's exactly why we have an ultimate, indestructible safety net. I introduced to you the quadratic formula. This is your foolproof backup plan, the absolute sledgehammer of your toolkit. If you can't find numbers that multiply perfectly to c and add to b, you just plug your a, b, and c values into this beautiful machine. It calculates the exact roots, where the equation hits 0, no matter how messy the decimals or fractions get. Once you have those roots, you just work backwards to write your factors out. It literally never, ever fails.
So there we have it. You now have a complete visual decision tree. You start by looking for a greatest common factor. You count your terms to see if you need trinomial rules, grouping, or SOFAS. And if all else fails, you have your quadratic backup plan. Armed with this master toolkit, you have everything you need to demystify algebraic chaos. But more importantly, you've learned how to look at an impossible, overwhelming problem, break it down to its core ingredients, and systematically solve it. So, what impossible problem will you unbake next? Keep practicing, and I'll see you on the next explainer.